Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring one of the strangest things science has ever discovered. Antimatter might sound like science fiction, but it is real, and it has properties that seem to turn the familiar world inside out. Antimatter asks one of the deepest questions in physics. Why is there something here rather than nothing? In the earliest moments of the universe, matter and antimatter may have been almost perfectly balanced, and in theory, should have totally annihilated each other. Yet somehow, matter survived. Every star, every planet, and every living thing depends on this one anomaly. Scientists can now create antimatter in laboratories and even contain it within extraordinary machines. They can even use it in medicine, where its brief flashes of energy help reveal what is happening inside the body. But antimatter is still surrounded by mystery. It appears to obey the same rules as matter, but it might also be a gateway into entirely new and undiscovered physics. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there's nothing you need to do but relax. Let your shoulders soften. Allow your breathing to slow. And as your mind begins to loosen its grip on the day, join me as we explore this fascinating world together. Let's begin. Antimatter is real matter with the opposite electric charge. It sounds as if it belongs to fiction, but it is part of the physical world. A particle of antimatter is not a ghost, a shadow, or a magical opposite. It has mass. It can carry energy. It can be created, measured, trapped, and studied. What makes it extraordinary is that its key electrical property is reversed. The antimatter partner of the electron carries a positive charge, even though it has the same mass as an electron. The antimatter partner of the proton carries a negative charge, while matching the proton's mass with astonishing precision. This simple reversal opens a doorway into some of the deepest questions in science. It means nature built a mirrored version of the particle world, governed by rules that look almost identical to our own. Somewhere inside that almost identical mirror lies a mystery. If the universe can make both versions, why did our familiar version become the one that fills the stars? A single gram of antimatter could release city-scale energy. The reason is not chemistry. It is not like burning fuel, splitting atoms, or storing power in a battery. It reaches deeper than that. When antimatter meets ordinary matter, the mass involved can be converted into energy with extreme efficiency. A gram sounds harmless, about the weight of a paperclip, yet its complete annihilation with a matching gram of matter would release an amount of energy far beyond any ordinary material. This is why antimatter appears so often in stories about future spacecraft. It is the most concentrated energy source that known physics allows. The problem is that making even tiny traces takes enormous machines, and storing it is almost absurdly difficult. It cannot touch a container, because the container is made of matter. So this astonishing power remains more like a scientific horizon than a practical tool. It shows us what reality permits, while reminding us how far engineering still has to travel. Matter and antimatter destroy each other when they meet. This meeting is not like a collision between two stones. It is more fundamental. The particles do not simply break apart into smaller pieces. They can vanish as particles and leave energy behind. In the case of an electron and its antimatter partner, the encounter usually produces gamma rays. These are forms of light, far more energetic than visible light. It is one of the clearest demonstrations that matter is not as solid and permanent as it feels. the familiar substance of the world can be transformed into radiation under the right conditions. This is also why antimatter cannot gather easily in our surroundings. Any stray antiparticle drifting through ordinary material is likely to meet its counterpart almost immediately. The result is brief, bright, and final. In laboratories, scientists use that final flash as evidence. The disappearance becomes a signal, and the signal tells them that a particle from the mirror side of nature was really there. The universe should contain far more antimatter than it does. According to our best understanding of the early universe, matter and antimatter should have been created together in nearly equal amounts. That expectation creates a stunning problem. If both sides had remained perfectly balanced, they would have met and annihilated on a cosmic scale. The universe would have been filled mostly with radiation, not stars, planets, oceans, or living beings. Yet when astronomers look into space, they do not see large regions made of antimatter. They see ordinary matter almost everywhere. Galaxies shine with ordinary atoms. Interstellar gas behaves like ordinary gas. Even the dust between stars appears to belong to our side of the mirror. Something must have tipped the balance at the beginning. It was not a large victory. It may have been a tiny preference hidden inside the laws of physics. But that tiny preference became everything. Every familiar object exists because the early universe failed to cancel itself completely. Scientists can make antimatter, but only in tiny amounts. Modern laboratories can create particles that almost never survive in the ordinary world. They do it by using high-energy collisions, where energy is concentrated so intensely that particle pairs can appear. These machines are not factories in the normal sense. They are more like precision instruments that persuade nature to reveal rare possibilities. The quantities produced are incredibly small. We are not talking about spoonfuls, grains, or even dust. We are talking about particles counted in numbers that sound large, but have a total mass that is almost nothing. This is why dramatic ideas about storing huge amounts of antimatter remain far from reality. The production process takes effort, power, and patience. It also produces many other particles at the same time, so the desired antiparticles must be separated and slowed. What makes the achievement remarkable is not the amount. It is the control. Humans can create fragments of the universe's missing mirror, then study them one by one. Antimatter exists naturally inside thunderstorms and cosmic ray collisions. High above the ground, nature sometimes becomes a particle accelerator. When energetic particles from space strike Earth's atmosphere, they trigger showers of new particles that can include antimatter. The process begins with violent impacts between fast-moving cosmic rays and atoms in the air. From those impacts, brief chains of creation unfold before the particles decay or vanish. Storms can also produce surprising bursts of high-energy radiation. In some cases, the electric fields inside thunderclouds accelerate electrons so strongly that gamma rays are produced. Those gamma rays can then create particle pairs, including positrons. For a moment, a familiar storm reaches into the same physics studied in giant laboratories. This does not mean the sky is filling with dangerous amounts of antimatter. The quantities are tiny, and the particles vanish quickly. Still, the idea is astonishing. Above ordinary rain and thunder, the atmosphere can briefly touch some of the most exotic behavior in the universe. Hospitals use antimatter particles to look inside living bodies. One of the most practical uses of antimatter is already part of modern medicine. In positron emission tomography, a patient receives a tracer containing atoms that release positrons as they decay. These positrons travel only a short distance before meeting electrons in the body. When that happens, they produce pairs of gamma-ray photons moving in opposite directions. A scanner detects those signals and uses them to build an image of activity inside the body. This is especially useful because the tracer does not simply show structure. It can reveal where certain biological processes are happening more intensely. Doctors can use this information to study the brain, examine the heart, or look for signs of disease. The wonder is that an event from particle physics becomes a medical tool. A tiny annihilation inside living tissue becomes a message that machines can read. Antimatter, often imagined as distant and dangerous, helps physicians see what ordinary light cannot. Every known particle appears to have an antimatter partner. The particle world comes with a remarkable kind of pairing. Electrons have positrons. Protons have antiprotons. Neutrinos have antineutrinos, although their story may still hold surprises. This pattern is not an extra decoration added to physics. It is built into the way modern theories describe particles. For many kinds of matter, the partner has the same mass but opposite electric charge. Other properties also reverse in precise ways. The discovery of these partners changed the meaning of matter itself. It showed that the familiar particles around us are only half of a larger design. Even particles with no electric charge can have antimatter versions, because charge is not the only property that matters. Physicists look at deeper labels carried by particles, such as baryon number or lepton number. The astonishing thing is not simply that antimatter exists. It is that nature seems to write its particle inventory with mirror entries, as though symmetry were part of the universe's grammar. Antimatter may hold clues to why anything exists at all. The greatest mystery is not how antimatter behaves in a laboratory. The greatest mystery is why the universe did not erase itself at the beginning. If matter and antimatter had been produced in exactly equal amounts, mutual annihilation would have left almost no material behind. Yet something remained. That leftover material became the cosmic web, the galaxies, and the chemistry that eventually made life possible. Antimatter is central to this question because it represents the missing side of the early balance. Scientists are searching for tiny differences between particles and antiparticles. A difference that seems insignificant in an experiment could have shaped the whole universe when everything was hot, dense, and rapidly changing. This turns antimatter into more than a strange substance. It becomes a clue about existence itself. Every measurement asks whether nature slightly prefers one side of the mirror. If it does, that preference may explain why there is a world here to ask the question. CERN traps antihydrogen to test the deepest rules of reality. At CERN, scientists do something that sounds almost impossible. They make atoms from antimatter and keep them from touching the walls of the experiment. The atom they study is antihydrogen, the counterpart of hydrogen. It is built from an antiproton and a positron. Because it has no overall electric charge, it cannot be held in the simplest particle traps. Researchers use carefully shaped magnetic fields, extreme vacuum, and very low temperatures to keep it suspended long enough to examine. The reason for choosing antihydrogen is beautifully direct. Hydrogen is the simplest atom in ordinary matter, and it has been measured with breathtaking precision. If antihydrogen differs from it in even a tiny way, physics may be missing something important. Scientists can shine lasers on trapped antihydrogen and compare its behavior with hydrogen. The goal is not to make large amounts. The goal is to ask whether the mirror really matches, down to the finest measurable detail. Paul Dirac predicted antimatter before anyone had ever seen it. In the late 1920s, Dirac was trying to combine quantum theory with Einstein's special relativity. The equation he found described the electron with remarkable power, but it also contained an unsettling possibility. It seemed to allow a particle like the electron with positive charge At first, this was not an easy idea to accept. Physics already had enough mysteries, and nobody had observed such a particle. Yet the mathematics was too elegant and too successful to ignore. Dirac's work suggested that the equations of nature were pointing beyond the known inventory of matter. A few years later, the predicted particle was discovered. This was one of the great moments when theory arrived before observation. A line of mathematics had revealed something real, waiting in the world. It showed that equations are not just tools for describing what we already know. Sometimes they act like lanterns, illuminating a part of reality before experiment catches up. The first antimatter particle was found in a cloud chamber. The discovery came through a device that made invisible particles leave visible trails. A cloud chamber contains vapor ready to condense when a charged particle passes through it. The path appears as a delicate track, like a signature written by something too small to see. In 1932, Carl Anderson was studying cosmic ray particles when he noticed a track that curved the wrong way for an electron in a magnetic field. Its curve showed that it had the electron's mass range, but a positive charge. This was the positron. The finding confirmed that Dirac's strange prediction was not just mathematics. It was a particle arriving from nature itself, born in high-energy processes above Earth. The image was modest compared with modern detectors, but its meaning was enormous. A thin track in vapor opened the door to a second side of matter. The universe had left a visible trace of its hidden symmetry. Positrons are antimatter versions of the electrons inside atoms. Every ordinary atom contains electrons around its nucleus, and those electrons help create chemistry. They form bonds, carry electric current, and shape the behavior of materials. A positron matches the electron in mass, but its charge is positive rather than negative. That reversal makes it both familiar and strange. If a positron enters ordinary matter, it does not last long. The world is filled with electrons, and an encounter is usually unavoidable. Yet before it disappears, a positron can reveal itself through the light produced by annihilation. Positrons appear in several natural and human-made settings. Certain radioactive decays release them. High-energy events in space can create them. Medical scanners use them. Their existence proves that the electron, one of the most common building blocks of everyday life, has a precise counterpart. It is astonishing to think that the particle responsible for ordinary electricity has a mirror partner that appears briefly, announces itself, and vanishes into radiation. Antiprotons have the same mass as protons, but opposite charge. A proton sits at the heart of every ordinary atom. It helps define the identity of each element, because the number of protons in a nucleus determines whether an atom is hydrogen, carbon, gold, or something else. The antiproton is its counterpart, with matching mass and negative electric charge. Creating one requires far more energy than creating a positron, because a proton is much heavier than an electron. This made the antiproton harder to discover. It was confirmed in the mid-1950s using powerful accelerator experiments. Once scientists could produce antiprotons, they gained a new way to test the symmetry of nature. Measurements compare their charge, mass, and magnetic behavior with those of protons. So far, the match is extraordinarily close. That closeness is both satisfying and frustrating. It supports the most successful theories of particle physics, yet it does not explain why ordinary protons fill the visible universe, while antiprotons are rare visitors. Antineutrons are neutral, yet their inner charges are reversed. A neutron has no overall electric charge, which might make its antimatter partner sound impossible to distinguish. But neutrality can hide structure. Neutrons are made of quarks, and those quarks carry fractional charges inside the particle. An antineutron is made of antiquarks, with the internal charges reversed. From the outside, both appear electrically neutral. Inside, they are mirror constructions. This shows why antimatter is not defined only by whether something is positive or negative. Some particles have deeper properties that reverse even when the total charge is zero. The antineutron was confirmed after the antiproton, and it helped strengthen the idea that whole families of particles have antimatter counterparts. Its existence is a lesson in subtlety. Nature can build two particles that look similar from a distance, yet differ profoundly in their inner bookkeeping. For physicists, that hidden reversal matters. It is part of the careful accounting that keeps the particle world consistent. Antimatter follows quantum rules as faithfully as ordinary matter. There is no special exception that makes antimatter chaotic or lawless. It belongs to the same quantum universe as everything else. Antiparticles can have wave properties. They can occupy allowed energy states. They can be described by quantum fields, probabilities, spins, and interactions. This is why scientists can make serious predictions about them rather than treating them as unpredictable oddities. When antihydrogen is studied, researchers expect it to absorb and emit light in patterns that match hydrogen, unless some hidden difference exists. When positrons move through matter, their behavior can be modeled with the same quantum care used for electrons. This faithfulness is what makes antimatter so powerful as a test of physics. If the rules apply exactly, our theories grow stronger. If they fail by even the smallest amount, something enormous may be waiting underneath. Antimatter is not interesting because it breaks every rule. It is interesting because it almost perfectly obeys them. The Big Bang may have created matter and antimatter equally. In the earliest stages of the universe, energy was packed into an incredibly hot and dense state. Under those conditions, particles could be created and destroyed constantly. Modern physics suggests that matter and antimatter should have emerged together, paired by the same processes that connect energy with mass. That idea creates one of the cleanest puzzles in cosmology. If the beginning treated both sides equally, the later universe should not be dominated by ordinary atoms. The early fire should have produced a great cancellation, leaving radiation as the main survivor. Instead, a small residue of matter endured. This does not mean the Big Bang theory is wrong. It means the story contains an additional chapter that scientists are still trying to read. Something in the early universe must have allowed equality to become imbalance. The answer may involve particle decays, hidden symmetries, or physics beyond current experiments. The origin of matter is still unfinished. A tiny imbalance may have saved the universe from vanishing. The survival of matter did not require a huge advantage. It may have required only a minute excess, the smallest preference repeated across an immense universe. Imagine countless particles and antiparticles annihilating in the early cosmos. Most pairs disappeared into radiation. Yet if there was a slight surplus of matter, then after the Great Cancellation, that surplus would remain. That leftover became the material for everything visible today. The scale of the idea is almost impossible to absorb. A difference far too small to notice in ordinary life may have decided whether galaxies could form at all. Scientists call this kind of process baryogenesis when it involves the origin of the matter excess. The details are still unknown, but the principle is captivating. The universe we know may not be here because matter won by strength. It may be here because matter won by the narrowest margin imaginable, and that margin became the entire observable world. Physicists call this cosmic mystery the matter-antimatter asymmetry. The phrase sounds technical, but the question behind it is simple and profound. Why does the visible universe contain so much matter and so little antimatter? An asymmetry is a mismatch between two sides that might have been expected to balance. In this case, the mismatch is cosmic. It is written across galaxies, stars, and interstellar gas. If large amounts of antimatter were mixed through space, astronomers would expect to see strong gamma-ray signals from annihilation where the two types met. Instead, the evidence points to a universe overwhelmingly made of ordinary matter. The challenge is to explain how that happened without breaking the successful parts of physics. Researchers study particle decays, symmetry violations, neutrino behavior, and conditions in the early universe. Each approach is a different attempt to find the missing tilt in nature's scales. The name may be formal, but the mystery is intimate. It is the reason matter had a future. Antimatter annihilation turns mass into pure packets of energy. Einstein showed that mass and energy are deeply connected. Antimatter makes that connection feel real. When a particle meets its matching antiparticle, the mass does not need to remain locked inside matter. It can emerge as energetic particles of light or other products allowed by conservation laws. This is different from ordinary chemical energy, where atoms rearrange and only a tiny fraction of mass is involved. Annihilation reaches into the identity of the particles themselves. For electrons and positrons, the result is often gamma-ray photons. For heavier particles, the outcome can include short-lived particles that quickly decay. The important point is that the original mass is transformed into something new and measurable. This is why annihilation is so central to both science and imagination. It reveals that matter is not the final form of substance. Under the right conditions, what seems solid can become radiation, and the boundary between material and energy becomes astonishingly thin. Electron-positron annihilation usually produces two gamma-ray photons. When these two particles meet at low energy, the result is often a perfectly balanced burst of radiation. Two photons fly away in opposite directions. This is not a decorative detail. It happens because nature keeps strict accounts. Energy must be conserved. Momentum must be conserved. The original particles had mass, and that mass becomes energy. But one photon alone could not usually carry the momentum correctly, so the event divides itself into a matched pair. This simple pattern is one reason positron annihilation is so useful. Scientists can look for two high-energy photons arriving from opposite directions and reconstruct where the meeting happened. In medicine, that geometry becomes an image. In physics, it becomes evidence. A vanishing particle pair leaves no fragments to hold, yet it writes its location in light. The event is brief beyond imagination, but the information it carries can travel through detectors, computers, and human understanding. Gamma rays from antimatter are among nature's most energetic light. They are not visible to the eye. They do not glow like candlelight, sunlight, or neon. They belong to the highest energy end of the electromagnetic spectrum, where each photon can carry far more energy than ordinary light. When antimatter annihilation produces gamma radiation, it gives scientists a clear signature that something extreme has happened. These photons can pass through matter more easily than visible light, although dense materials can still absorb or scatter them. That penetrating power makes them useful and difficult at the same time. Instruments must be designed carefully, because gamma rays do not behave like simple rays in a telescope lens. They often need special detectors that register the energy they leave behind. In astronomy, gamma rays can point toward violent events in space. In laboratory physics, they reveal particle transformations. They remind us that light is not always soft or familiar. Sometimes light is the final messenger of matter turning into energy. Particle accelerators create antimatter by concentrating enormous collision energy. Inside an accelerator, particles are pushed to incredible speeds and guided into carefully chosen targets or opposing beams. The goal is not to smash things randomly. It is to focus energy into a tiny region where nature can convert some of that energy into new particles. Antimatter can appear this way because mass and energy are interchangeable under the right conditions. The machine must first give ordinary particles enough kinetic energy to cross the threshold for creating heavier pairs. After the collision, detectors search through the debris for the rare particles of interest. This is a little like recreating a tiny fragment of the early universe under controlled conditions. It requires magnets, timing systems, vacuum pipes, and extraordinary precision. The antimatter is not carved out of existing material. It is born from concentrated energy during an instant of collision. That is part of the wonder. Human engineering can create conditions where reality briefly expands its particle inventory. Most manufactured antimatter disappears almost as soon as it forms. The problem begins the moment an antiparticle is created. The laboratory around it is made of ordinary matter, from the walls of the beam pipe to the faintest leftover gas inside the vacuum. If the antiparticle touches any suitable counterpart, it is gone. Many newly created particles are also moving extremely fast, which makes them harder to capture. They may race through detectors, collide with material, or decay before they can be stored. Scientists therefore need to select, slow, cool, and guide the particles with great care. Even then, only a fraction can be kept long enough for detailed study. The rest amount themselves through tracks, flashes, or deposited energy, then vanish. This is why antimatter research often feels like studying lightning trapped in mathematics. The particles are real, but their lives in ordinary surroundings are usually brief. Each successful capture represents a victory over speed, contact, and the constant pressure of the material world. Magnetic fields can hold charged antimatter away from ordinary walls. A charged particle responds to magnetism because its motion and charge connected to electromagnetic force. Scientists use this fact to create invisible containers. Instead of placing antimatter in a physical vessel, they shape electric and magnetic fields so the particle spirals, bounces, or remains confined in open space. This keeps it from touching matter and disappearing. The technique works best with charged particles, such as positrons or antiprotons. The fields must be stable, clean, and precisely arranged. A small imperfection can let particles drift away. The surrounding vacuum must also be extremely good, because even a stray atom can end the experiment. These traps are remarkable because they show how a container does not always need solid walls. It can be made from force itself. In such devices, antimatter is not held by glass, metal, or plastic. It is held by carefully sculpted physics, suspended inside a space that must remain almost empty. Neutral antihydrogen is harder to trap than charged antiprotons. Once an antimatter atom has no overall electric charge, it no longer responds strongly to the same trapping methods used for charged particles. This creates a serious challenge. Antiprotons can be guided and confined with electromagnetic fields because their negative charge gives experimenters a handle. Antihydrogen is more elusive. It can still interact with magnetic fields, but only through much weaker effects connected to its internal magnetic properties. To trap it, scientists must make the atoms very cold, because fast atoms escape too easily. They must also create a magnetic bottle that is strong enough to influence neutral atoms without letting them touch the apparatus. This is delicate work. The reward is enormous, because an antimatter atom can be compared with the simplest ordinary atom in ways that isolated particles cannot. Trapping it means gaining time. Time allows laser measurements, gravity tests, and careful questions about whether nature treats both atomic mirrors exactly the same. Antimatter cannot be stored in an ordinary bottle or tank. The reason is beautifully unforgiving. Any normal container is made of atoms. The inside surface may look smooth, polished, and sealed, but at the particle level, it is ordinary matter waiting everywhere. If antimatter touched it, the storage attempt would end immediately. This makes familiar ideas about fuel tanks useless. You could not pour antimatter into a cylinder, seal the lid, and carry it away. Even a perfect physical wall would be the wrong kind of wall. Scientists must instead use traps that prevent contact, usually by relying on fields and vacuum. This also means storage becomes harder as the amount increases. More particles bring more motion, more mutual effects, and more chances for loss. Antimatter storage is therefore not just an engineering problem. It is a direct confrontation with the basic nature of matter. To keep antimatter, you must create a place where almost nothing ordinary can touch it at all. The Alpha experiment has trapped antihydrogen for many minutes. This achievement is extraordinary because an antiatom is fragile in ordinary surroundings. The experiment must first gather antiprotons and positrons, then bring them together under conditions cold enough for antihydrogen to form. After that, the neutral antiatoms must remain confined by magnetic fields that act on their tiny magnetic properties. Holding them for many minutes gives researchers something precious. It gives them time to examine antimatter as an atom, not just as a fleeting particle track. The longer the confinement lasts, the more carefully scientists can study how antihydrogen absorbs light, how it behaves under gravity, and whether its properties match hydrogen. Every trapped antiatom is surrounded by risk. A collision with the apparatus would destroy it. Yet with patience and refined control, researchers have turned something once considered almost impossible into a repeatable experimental method. The result is not a dramatic quantity of antimatter. It is something deeper, a chance to question reality with precision. Antihydrogen contains one antiproton orbited by one positron. This makes it the antimatter counterpart of the simplest ordinary atom. Hydrogen has one proton and one electron. Replace each particle with its antimatter partner, and the mirrored atom appears. The antiproton forms the central nucleus. The positron occupies the surrounding quantum state. That simple structure is why antihydrogen matters so much to physics. A complicated atom would introduce many layers of interaction, which could make subtle differences harder to interpret. A simple atom gives scientists a cleaner comparison. Hydrogen has been measured with astonishing precision for generations. Its spectral lines are among the best-known fingerprints in science. By measuring antihydrogen, researchers can ask whether the same fingerprint appears in the antimatter world. It is a quiet but profound test. If the positron's energy levels around an antiproton match the electron's levels around a proton, symmetry survives another challenge. If not, the smallest atom in the mirror may reveal a crack in our deepest laws. Scientists compare hydrogen and antihydrogen to test cosmic symmetry. The comparison rests on a powerful idea. The laws of physics may remain unchanged if matter is replaced with antimatter, space is mirrored, and time is reversed together. This principle is known as CPT symmetry. It is one of the pillars beneath modern particle theory. Hydrogen and antihydrogen provide an elegant test because they are simple, measurable, and directly related. Scientists can study the light each atom absorbs or emits. If their spectral behavior differs, even by a tiny amount, it could mean that one of the foundations of known physics needs revision. The measurements are extremely demanding. The antiatoms must be produced, cooled, trapped, and probed without touching matter. The experiment is not trying to confirm a dramatic visual difference. It is searching for a microscopic mismatch in nature's handwriting. That is what makes it so exciting. A nearly invisible shift in an atomic line could point toward a deeper theory of the universe. Antimatter seems to fall downward under gravity, like matter. For many years, this question remained surprisingly difficult to answer directly. Antimatter has mass, so physicists expected gravity to attract it. Still, expectation is not the same as measurement. Charged antiparticles are strongly affected by electric and magnetic fields, and those effects can overwhelm the tiny pull of Earth's gravity. Neutral antihydrogen offered a better path because it is less easily disturbed by electric fields. Researchers could release trapped antiatoms and observe where they went. The results showed that they tended to move downward under Earth's gravity, within the limits of the experiment. This may sound ordinary, but it closed a door on some very strange possibilities. If antimatter had fallen upward, physics would have faced a revolution. Instead, the result suggests that gravity treats antimatter much like matter. Even so, the story is not finished. Scientists still want more precise measurements because the exact strength of that fall may carry deeper information. That falling test was a milestone for modern physics. The importance lies in how hard the question was to ask cleanly. Gravity is the weakest of the fundamental forces at particle scales, while electromagnetic forces are vastly stronger. A tiny patch of unwanted electric charge can disturb a measurement. A small magnetic imperfection can shift the path. Even the energy of the trapped atoms matters. To watch antihydrogen respond to gravity, scientists had to produce neutral antiatoms, cool them, confine them, release them, and detect their annihilation positions. Each step required years of refinement. The outcome did not merely satisfy curiosity. It brought antimatter into a test that had once belonged mostly to theory. It showed that experimental physics can reach even the most delicate questions when the tools become precise enough. The achievement also gave future experiments a foundation. Now researchers can improve the method, reduce uncertainties, and ask whether antimatter's gravitational behavior matches ordinary matter with exquisite accuracy. Antimatter engines remain far beyond our current engineering abilities. The appeal is easy to understand. If mass can be converted into energy so efficiently, antimatter sounds like the ultimate fuel. A spacecraft powered by it could, in principle, get far more energy from less material than chemical rockets ever could. But the practical obstacles are enormous. We cannot produce antimatter in large quantities. We cannot store it safely in bulk. We cannot yet turn annihilation products into controlled thrust with the required efficiency. Many annihilation events produce radiation or particles that are difficult to direct. The useful engine would need to contain the reaction, protect the spacecraft, and channel the energy into motion without destroying the machine. Each of those requirements is formidable by itself. Together, they place antimatter propulsion far beyond today's technology. Still, the concept remains valuable. It gives engineers and physicists a boundary to imagine against. It asks what space travel might become if we ever learned to manage the most intense fuel known. Science fiction starships made antimatter famous long before laboratories did. For many people, the first encounter with antimatter came through stories, not textbooks. Writers recognized its dramatic power immediately. It was real enough to sound scientific, strange enough to feel futuristic, and energetic enough to move imaginary vessels across impossible distances. Fiction often simplified the details. It treated antimatter as a fuel that could be stored, regulated, and used with confidence. Real physics is much less convenient. Yet these stories did something important. They carried a genuine scientific idea into public imagination. They made audiences wonder what happens when matter meets its opposite. they turned a difficult particle physics concept into a symbol of advanced civilization. That symbol still shapes how people talk about future technology. The laboratory version is smaller, colder, and far more delicate than fiction suggests. But the fascination is not misplaced. Antimatter really does touch the edge of what energy, matter, and engineering might mean. Real antimatter propulsion would require impossible levels of storage. A useful spacecraft would need more than the ability to create a few antiparticles. It would need a dependable supply that could survive launch, flight, vibration, temperature changes, and long missions. That is where the idea becomes brutally difficult. Antimatter must be kept from touching ordinary matter at every moment. For charged particles, fields can provide confinement, but a propulsion system would need much larger amounts than laboratory traps can handle. Neutral antiatoms bring different challenges because they are harder to control. The storage device would also need power, shielding, and fail-safe systems. Any loss would waste the fuel and could damage equipment. Even if production somehow became easier, containment would remain a central barrier. The problem is not that antimatter lacks energy. It has almost too much. The real challenge is holding that energy in a form that can wait patiently until a spacecraft needs it. The cost of making antimatter is almost unimaginably high. This is not because antimatter is rare in a market sense, like a precious metal hidden in rock. It is expensive because making it requires large scientific facilities, powerful beams, advanced magnets, cryogenic systems, vacuum technology, and teams of specialists. The process is also inefficient. Only a small fraction of the energy put into particle collisions becomes useful antimatter that can be collected. Much of the energy goes into other particles, heat, radiation, and machine operation. Then the antiparticles must be slowed and captured, which adds more complexity. When people hear claims about antimatter being the most expensive substance, the exact number depends on assumptions. The basic point remains true. It is not remotely practical to manufacture in meaningful quantities today. The expense reflects the difficulty of forcing nature into rare conditions. Each tiny amount represents a chain of machinery and expertise, not a material that can simply be mined, refined, or bottled. Antimatter is not dangerous in nature because it is scarce. The word often sounds alarming, partly because annihilation is such a powerful process. In the natural world, however, antimatter appears only in tiny, fleeting amounts. Positrons may be produced by radioactive decay, cosmic ray interactions, or energetic atmospheric events. These particles do not accumulate into hidden clouds or dangerous deposits. They quickly encounter ordinary matter or decay processes that remove them from the scene. The scale matters. A single antiparticle annihilation is detectable with instruments, but it is not a threat to everyday life. Nature is full of small, high-energy events happening constantly at the particle level. Our bodies, the air, and the ground all contain traces of natural radioactivity. That does not mean they are dangerous in ordinary conditions. Antimatter's reputation comes from what large quantities could do, not from what nature actually provides nearby. Around us, it is more like a brief scientific whisper than a stored cosmic hazard. Natural antimatter usually annihilates before it can gather together. To form a lasting object, antiparticles would need to meet one another and avoid ordinary matter long enough to assemble. That is incredibly unlikely in our environment. Ordinary matter fills the air, the ground, the oceans, and interplanetary dust. Even space is not perfectly empty. A positron created by a decay or collision has many chances to meet an electron before it ever joins a larger antimatter structure. Antiprotons face similar obstacles. They may be produced in high-energy collisions, but they move through regions that contain magnetic fields, radiation, and matter. Instead of building antiatoms in abundance, they usually disappear through interactions. This is one reason the universe around us looks so one-sided. Locally, antimatter is not given the peaceful conditions required for accumulation. It is born in flashes and erased by contact. Nature can create the ingredients, but the ordinary material world makes it very hard for them to gather. Bananas release tiny traces of antimatter from radioactive potassium decay. This fact is surprising because bananas feel so ordinary. They contain potassium, which is an essential element for living cells. A small fraction of natural potassium is the radioactive isotope potassium-40. Most of its decays do not produce positrons, but a rare branch can. When that happens, a positron is emitted from the atom. It soon meets an electron nearby and annihilates. The amount involved is incredibly small and harmless. The point is not that bananas are dangerous. They are not. The point is that antimatter is not only found in distant laboratories or violent regions of space. It can appear in the quiet chemistry of everyday life, created by a natural isotope inside a familiar fruit. This makes the universe feel stranger in the best possible way. Something from the world of particle physics can occur on a kitchen counter, not as spectacle, but as a tiny event hidden inside ordinary matter. Your own body emits occasional positrons from natural radioactive isotopes. Human bodies contain elements gathered from food, water, and the environment. Among them are tiny amounts of naturally radioactive isotopes. Some can produce positrons in rare decay processes. The activity is extremely low and part of the ordinary background of natural radioactivity that surrounds life on Earth. There is no reason to imagine the body as glowing with antimatter. These events are sparse, microscopic, and harmless at normal levels. Yet they are fascinating because they place particle physics inside biology. The atoms in a living body do not all sit permanently still. Some transform according to nuclear rules, independent of heartbeat, thought, or intention. When a positron appears, it travels a short distance and then vanishes in an encounter with an electron. The body never notices, but physics does. It is a reminder that living tissue is made from the same quantum materials as stars, rocks, and laboratory detectors. PET scans use positrons to map activity inside the brain. The power of this technique comes from metabolism. Doctors can use a tracer linked to a molecule that active cells take up. In brain imaging, one common approach follows glucose use, because busy nerve tissue needs energy. The tracer contains a radioactive atom that emits a positron. After annihilation, the scanner detects paired gamma photons and reconstructs where the decay occurred. Areas with stronger tracer uptake can reveal patterns of activity or disease. This does not photograph thoughts. It maps biological processes that support brain function. That distinction matters because the image is powerful, but not magical. It can help clinicians and researchers study conditions involving memory, movement, seizures, tumors, and degeneration. The wonder is that a particle from antimatter becomes part of a diagnostic chain. A positron lives for only a short time in tissue, but the light from its disappearance helps build a picture of one of the most complex structures in nature. Antimatter medicine depends on annihilation light escaping the body. For a scanner to work, the signal must get out. When positrons annihilate inside tissue, the gamma photons travel outward in nearly opposite directions. Some are absorbed or scattered, but many leave the body and reach detector rings around the patient. The scanner records pairs that arrive at almost the same time. From those paired detections, it calculates a line along which the annihilation occurred. Many lines combine into a three-dimensional map. This is a beautiful example of geometry becoming medicine. The patient does not need to feel the individual events. The machine gathers countless tiny signals and turns them into information. The method depends on the fact that gamma photons can pass through tissue better than visible light. Without that escape, the image would remain trapped inside the body. Antimatter's role is brief, but essential. Its disappearance creates the messenger that carries hidden biological activity into the reach of human sight. Cosmic rays constantly make antimatter high in Earth's atmosphere. Space sends a steady rain of energetic particles toward our planet. Many are protons or atomic nuclei moving at tremendous speeds. When they strike atoms in the upper atmosphere, the impacts create showers of secondary particles. Some of those particles decay into other particles, and antimatter can appear in the chain. Positrons are especially common among the products. Antiprotons can also be produced when collision energies are high enough. Most of this happens far above everyday weather. By the time the cascade reaches lower altitudes, many particles have decayed, scattered, or annihilated. Scientists study these atmospheric showers to understand both cosmic rays and particle physics. The atmosphere becomes a giant detector, transforming invisible visitors from space into measurable events. Every moment, Earth is being touched by high-energy particles from beyond the planet. Their collisions briefly create fragments of the antimatter world, then fold those fragments back into the ordinary matter surrounding us. Some satellites have detected antimatter particles trapped near Earth. Earth's magnetic field does more than guide compass needles. It also shapes the movement of charged particles around the planet. In certain regions, particles can become trapped, spiraling along magnetic field lines and bouncing between hemispheres. Spacecraft have detected antiprotons in these radiation belts, created when cosmic rays strike the upper atmosphere and produce secondary particles. Some of those antiparticles become temporarily confined by the magnetic environment. The quantities are tiny, but the discovery is remarkable. It means Earth is not only a passive target for cosmic rays, it can also hold a sparse population of exotic particles in its magnetic surroundings. These trapped antiparticles do not form a usable reservoir. They are far too few and too difficult to collect. But they show how planetary magnetism can organize particle motion on a grand scale. Around our familiar world, invisible fields can briefly turn the aftermath of cosmic collisions into a natural antimatter trap. Thunderstorms can launch positron beams upward into the atmosphere. A storm cloud may look like a weather system, but inside it, there can be powerful electric fields. Under certain conditions, electrons are accelerated to very high energies. When they interact with air molecules, they can produce bursts of gamma radiation. Those gamma rays may create electron-positron pairs. Some positrons then travel along magnetic field lines, sometimes upward from the storm region. Satellites have observed signals linked to these events, known as terrestrial gamma-ray flashes. They show that thunderstorms can produce particle physics normally associated with accelerators and cosmic phenomena. This does not mean lightning storms are filled with dangerous antimatter. The amounts are tiny and short-lived. The astonishing part is the connection. A storm above the tropical ocean or continent can briefly generate antimatter particles and send them into near space. What seems like ordinary lightning is part of a deeper electrical engine, one that can touch nuclear and particle processes. Lightning physics briefly reaches into the world of antimatter. A lightning flash is not just a visible spark. It is the outcome of charge separation, electric breakdown, and rapid particle acceleration inside air. In extreme cases, the fields near storms can push electrons so hard that they produce radiation energetic enough to trigger pair creation. That process belongs to the same family of physics used to explain antimatter production elsewhere. The storm is not controlled like a laboratory. It is turbulent, unpredictable, and spread across enormous volumes. Yet for a fraction of a second, it can create conditions where high-energy photons turn into matter and antimatter pairs. This makes lightning more than a weather spectacle. It becomes a natural bridge between atmospheric science and particle physics. The sky above us is not only a place of clouds and rain. It is also a charged environment where rare events reveal how energy can transform into particles, even within the air of our own planet. The Sun produces positrons during some nuclear reactions in its core. Deep inside the Sun, pressure and temperature allow nuclear fusion to proceed. Hydrogen nuclei are transformed through a chain of reactions that ultimately releases energy and builds helium. In part of this process, a proton changes into a neutron through a weak interaction. That transformation emits a positron along with a neutrino. The positron does not travel far in the solar core. The surrounding plasma is dense with electrons, so annihilation follows quickly. The energy from these events joins the broader flow that slowly works outward through the Sun before eventually escaping as sunlight. This means antimatter participates in the hidden engine that warms Earth. It is not stored there as a separate substance. It is created and erased as part of the fusion sequence. Every day, the light falling on your skin is connected to nuclear reactions in which positrons briefly appear at the center of our star. Supernova explosions can create antimatter through violent nuclear processes. When a massive star dies, its final collapse and explosion create some of the most extreme conditions in the universe. Temperatures soar, densities change rapidly. Nuclear reactions forge unstable isotopes that later decay. Some of those decays release positrons. These particles may annihilate nearby, adding to the high-energy radiation associated with the explosion and its aftermath. Supernova also send shock waves through surrounding gas, accelerate particles, and seed space with elements made in the star's final stages. Antimatter is only one part of that grand event, but it is a revealing part. It shows that stellar death is not merely destruction. It is a factory of transformation. The atoms scattered into space include ingredients for future stars and planets. At the same time, short-lived antiparticles appear and vanish in the expanding debris. In a supernova, matter is crushed, remade, expelled, and briefly mirrored under conditions no laboratory can fully reproduce. Black holes may surround themselves with antimatter-producing particle jets. Near a feeding black hole, matter can become extremely hot before crossing the event horizon. It swirls in an accretion disk, where magnetic fields and friction help release tremendous energy. Some systems launch narrow jets that shoot particles outward at nearly the speed of light. In such environments, gamma rays and energetic particle collisions can create electron-positron pairs. The antimatter does not come from inside the black hole. It forms in the intense region around it, where radiation and fields are powerful enough to drive exotic processes. These jets can stretch across vast distances and influence the gas around galaxies. They are among the most dramatic structures in astrophysics. Antimatter may be woven into their particle flow, especially in the form of positrons. The idea is stunning because black holes are often imagined as endings. Around them, however, nature can create some of its fastest outflows and most energetic particle transformations. The Milky Way glows with mysterious positron annihilation light. Astronomers have detected a gamma-ray signal from the central region of our galaxy that matches the energy expected when positrons meet electrons. This glow has been studied for decades, and its source remains debated. It is not a glow the eye could see. It is a high-energy signature measured by specialized instruments in space. The signal suggests that positrons are being produced somewhere in or near the galactic center. then slowing down and annihilating. The challenge is explaining where enough of them come from. Possible sources include certain stellar explosions, compact objects, and energetic environments near the heart of the galaxy. Each candidate has strengths and problems. That uncertainty makes the glow fascinating. It is as though the Milky Way is carrying a hidden particle process in its central regions. The light is not bright in a familiar sense, but it is a clue written in gamma rays across the galaxy. Astronomers still debate the source of galactic antimatter signals. The mystery persists because the gamma ray pattern must be matched to real astrophysical sources. Positrons might come from radioactive isotopes made in stellar explosions. They might be produced near compact objects such as neutron stars or black holes. Some theories have even explored more exotic origins, although ordinary astrophysical explanations remain important. The difficulty is that positrons can travel before annihilating, so the place where the signal appears may not be exactly where the particles were born. The central region of the Milky Way is also crowded and complex. It contains old stars, gas clouds, magnetic fields, and energetic sources, packed into a difficult observing environment. Astronomers must combine gamma-ray maps with models of particle motion and source populations. The debate is not a failure. It is the scientific process working at galactic scale. A signal has been found, but the story behind it is still being assembled. Pulsars may be natural factories for electrons and positrons. A pulsar is a rapidly spinning neutron star with an intense magnetic field. Around it, electric fields can accelerate particles to extraordinary energies. In those conditions, high-energy photons can produce cascades of electron-positron pairs. The result is a magnetosphere filled with charged particles moving along magnetic field lines. Some escape into surrounding space as a pulsar wind. This makes pulsars important suspects in several high-energy astrophysical puzzles. They can inject positrons into the galaxy, and nearby pulsars may contribute to the antimatter particles detected in cosmic rays. The environment is difficult to imagine. A city-sized stellar remnant spins with enormous precision while its magnetic field sweeps through space like a cosmic beacon. Yet the physics around it is not merely decorative. It can manufacture particles from radiation and acceleration. Pulsars show that antimatter is not only made by human machines. Nature builds far more powerful accelerators from collapsed stars. Dark matter searches sometimes look for unexpected antimatter particles. Dark matter does not shine, absorb light, or reveal itself through ordinary telescopes. We infer it mainly from gravity. Still, some theories suggest that dark matter particles might occasionally collide or decay into ordinary particles, including antimatter. If that happened, detectors in space might see extra positrons, antiprotons, or even antinuclei, beyond what normal astrophysical processes can explain. This makes antimatter a possible messenger from something invisible. The challenge is separating a truly unusual signal from the background created by cosmic rays, pulsars, supernova remnants, and other energetic sources. Scientists look for patterns in energy, direction, and abundance. A surprising excess can be exciting, but it must be tested against many possible explanations. This work shows how antimatter can act like a detective clue. It may not reveal dark matter directly, but it can help narrow the search. In the right pattern, a rare antiparticle could point toward one of the universe's greatest hidden components. Antimatter can help reveal hidden events in deep space. Because antimatter often produces distinctive radiation when it disappears, it can act as a marker for processes that would otherwise be hard to see. A positron created by radioactive decay, a compact object, or an energetic collision may not survive long. but its annihilation can leave photons that travel across space. Those photons can carry information about the environment where the particle slowed and vanished. Scientists use such signals to study violent or unusual regions that ordinary visible light may not fully explain. Antimatter also appears in cosmic rays, which bring samples of high-energy particle processes directly to detectors near Earth. Each antiparticle is like a messenger from an unseen event. It may have been born in a stellar explosion, a pulsar wind, or a collision far above the atmosphere. By studying these arrivals, researchers learn about places they cannot visit and events that happened long before the signal reached us. Astronomers still debate the source of galactic antimatter signals. The puzzle is not whether the signal exists. The puzzle is what keeps feeding it. Near the center of the Milky Way, instruments have detected radiation linked to positrons meeting electrons. That tells scientists that antimatter is being produced somewhere in the crowded heart of our galaxy. But the galactic center is a complicated place. It contains dense star fields, old stellar remnants, gas clouds, magnetic structures, and energetic objects packed into a region that is difficult to untangle. Several suspects could contribute. Some dying stars create radioactive atoms that later release positrons. Compact objects may accelerate particles in extreme magnetic fields. Ancient stellar populations may be involved. Each explanation solves part of the mystery while leaving awkward gaps. The difficulty is that positrons can travel before they vanish, so the glow may not point directly to their birthplace. It is a detective story written in high-energy light, with the crime scene spread across thousands of light-years. Pulsars may be natural factories for electrons and positrons. A pulsar begins as the collapsed core of a massive star. It is small enough to fit near a city, yet it can contain more mass than the Sun. Around it, magnetic fields become almost unimaginably strong. As the star spins, those fields sweep through space and accelerate particles to extreme energies. In that environment, high-energy radiation can transform into pairs of matter and antimatter particles. A single particle can trigger a cascade, multiplying into a storm of electrons and positrons. This process helps explain why pulsars shine across the electromagnetic spectrum. It may also explain some of the antimatter detected in cosmic rays near Earth. The most fascinating part is the scale. A dead star, crushed into a dense remnant, can behave like a cosmic electrical machine. It takes rotation, magnetism, and gravity, then turns them into beams of radiation and particles that travel far beyond the star itself. Dark matter searches sometimes look for unexpected antimatter particles. Dark matter cannot be seen directly, so scientists search for its fingerprints. One possible fingerprint would be an unusual excess of antimatter in space. Some theories suggest that dark matter particles could occasionally collide with each other or decay into ordinary particles. Those products might include positrons, antiprotons, or even heavier antimatter nuclei. Detectors placed on satellites, balloons, and space stations can count these rare visitors as they arrive near Earth. The challenge is interpretation. Ordinary astrophysical objects can also produce antimatter, so an excess is not automatically a discovery of dark matter. Researchers must compare the energy pattern, direction, and abundance with known sources. A convincing signal would need to stand apart from pulsars, cosmic ray collisions, and stellar explosions. That makes the search painstaking, but thrilling. Antimatter becomes a possible clue from something invisible. A particle that survives the journey to our detectors may carry news from the hidden mass-shaping galaxies. Antimatter can help reveal hidden events in deep space. The universe often hides its most energetic processes behind distance, dust, or darkness. Antimatter can act as a messenger from those concealed places. When positrons or antiprotons are created, they usually come from events powerful enough to reshape particles themselves. Their later interactions can produce signals that telescopes detect long after the original event has faded. This allows scientists to study environments that visible light alone cannot explain. A burst of gamma radiation may point toward radioactive decay and stellar debris. A rare antiproton in cosmic rays may hint at a collision involving particles moving close to light speed. A possible antimatter nucleus could tell researchers about violent regions that assemble particles in unusual ways. Each clue must be handled carefully because space contains many overlapping sources. Still, antimatter gives astronomy another sense to work with. It lets scientists listen for particle transformations occurring far beyond the reach of ordinary images. Antiprotons found in cosmic rays carry clues from extreme collisions. Cosmic rays are not rays in the everyday sense. Many are fast-moving particles that travel through space before striking detectors or Earth's atmosphere. Among them are rare antiprotons. These are usually thought to form when high-energy cosmic particles slam into gas between stars. The collision can create new particle pairs, including protons and antiprotons. Because antiprotons are uncommon, their energies and numbers are valuable. They help scientists understand how cosmic rays move through the galaxy, how they interact with interstellar material, and how magnetic fields scatter their paths. Some researchers also watch for antiprotons that do not fit ordinary expectations. An unexpected pattern could point toward a more exotic source. The difficulty is that every antiproton arrives without a label. It does not tell us where it was born. Scientists must reconstruct its story from statistics, models, and careful measurements, turning rare particles into evidence about the galaxy's hidden violence. No confirmed antimatter galaxy has ever been discovered. It is possible to imagine a galaxy made entirely of antimatter, with antistars, antiplanets, and antiatoms behaving much like ordinary matter from a distance. But evidence for such a place has never been confirmed. The reason scientists doubt nearby antimatter galaxies is contact. Space between galaxies is thin, but it is not empty. If a large antimatter region bordered ordinary matter, particles meeting at the boundary should produce powerful gamma-ray signals. Astronomers have searched for signs of this kind of large-scale annihilation, and they have not found convincing evidence. This does not prove that no antimatter exists anywhere in the entire universe. It does show that our observable neighborhood is overwhelmingly made of ordinary matter. That absence matters. It forces cosmology to explain why the early universe did not separate neatly into huge matter and antimatter domains. The missing antimatter galaxy is not just an empty discovery. It is a clue about cosmic history. An antimatter star would look strangely normal from far away. From a distance, light from a mantis star would not carry a simple label saying it came from antimatter. Antihydrogen would have the same expected spectral pattern as hydrogen, unless extremely tiny differences exist. Nuclear fusion inside an antistar would release energy in ways broadly similar to fusion inside an ordinary star. Its gravity would attract nearby objects. Its surface could shine. To an optical telescope, it might appear like an ordinary point of starlight. The giveaway would come from its surroundings. If ordinary gas fell onto it, matter and antimatter would meet near its outer layers and produce gamma rays. That high-energy signature could reveal what visible light conceals. This makes the search subtle. Scientists cannot simply look for a star with an opposite color or reversed brightness. They must hunt for unusual radiation patterns around objects that otherwise behave normally. The idea is strange because an antistar could hide in plain sight, shining like any other star. contact between matter gas and antimatter stars would glow brightly. Interstellar space contains thin gas, drifting atoms, and small particles. If an antimatter star moved through such material, the surrounding ordinary matter would not settle quietly onto its surface. It would annihilate when it encountered antimatter. That contact should produce energetic radiation, especially gamma rays. The pattern might form a kind of high-energy halo or signal around the object. Scientists can search for such clues when considering whether any unusual stars might be made of antimatter. The amount of radiation would depend on the density of nearby gas and the motion of the star through space. In a very empty region, the signal might be weak. In a denser environment, it could become much more obvious. This is why the absence of clear signals matters. It does not merely say that antimatter stars are hard to find. It suggests that if they exist in our galaxy, they must be rare, hidden, or in unusually quiet surroundings. Gamma-ray telescopes search for signs of distant antimatter regions. Ordinary telescopes gather visible light, but antimatter often announces itself in much more energetic radiation. To find possible distant antimatter regions, scientists use instruments designed to detect gamma rays. These telescopes are usually placed in space because Earth's atmosphere blocks much of this radiation before it reaches the ground. The instruments measure photon energies, arrival directions, and sky patterns. Researchers then look for signatures that match matter-antimatter annihilation. This is not a simple treasure hunt. Many astrophysical processes produce gamma rays, including pulsars, supernova remnants, and black hole environments. A candidate signal must be distinguished from all those sources. Large antimatter domains would be especially interesting because their borders with ordinary matter should glow where particles meet. So far, observations have placed strong limits on how much antimatter can be nearby in cosmic terms. The search continues because gamma rays can reveal what ordinary starlight might completely miss. The absence of antimatter galaxies is itself a cosmic clue. Sometimes science learns from what is missing. If the universe had created equal amounts of matter and antimatter, one might imagine vast regions of each surviving separately. But the sky does not show the expected boundary glow from large nearby antimatter domains. This absence tells physicists that the imbalance was probably not just a local accident. It appears to be a feature of the observable universe. That pushes the mystery deeper into the laws of particle physics and the earliest moments of cosmic history. The missing galaxies also help rule out simpler explanations. It is not enough to say that antimatter is far away, unless it is so far that its signals are beyond observation. Within the universe we can study, matter dominates. This fact turns every galaxy into evidence. The stars are not only beautiful structures, they are witnesses to an ancient imbalance that chose one side of matter almost everywhere we can see. Charge symmetry says antimatter mirrors matter in electric charge. In physics, symmetry is not just about visual beauty. It is about whether the rules remain consistent after a transformation. Charge symmetry asks what happens if every particle is replaced by its antiparticle. Positive charges become negative. Negative charges become positive. Other charge-like properties reverse as well. If the laws looked exactly the same after that exchange, charge symmetry would be perfect. Nature comes close in many situations, which is why antimatter can resemble matter so closely. But close is not the same as exact. Some weak interactions do not respect this symmetry by itself. That discovery mattered because it showed that the mirror between matter and antimatter contains fine cracks. Those cracks may be small, but small differences can become cosmically important under early universe conditions. Charge symmetry gives scientists a language for asking whether nature treats the two sides equally, or whether a hidden preference shaped everything that followed. Parity symmetry asks whether mirror-reflected physics stays unchanged. Imagine watching a physical process in a mirror. If the mirrored version could happen in nature with the same probability, then parity symmetry would hold. For a long time, many scientists assumed this must be true. Space seemed to have no built-in preference for left or right. Then experiments involving the weak nuclear force showed otherwise. Certain particle processes reveal a handedness. They behave differently from their mirror-reflected versions. This was shocking because it meant that nature itself can distinguish between left and right at a fundamental level. Parity violation is not something we notice in everyday objects, where countless interactions average together. It appears in the delicate behavior of subatomic particles. Its importance for antimatter lies in the broader question of symmetry. If nature can break mirror symmetry, then perhaps other near symmetries can break too. The universe may look balanced at first glance, while its smallest rules contain hidden direction. Time symmetry imagines physical processes running backward in time. Many everyday events clearly look different in reverse. A broken cup does not leap back onto a table. Smoke does not gather neatly into a flame. Yet at the level of fundamental equations, some processes can appear surprisingly reversible. Time symmetry asks whether the laws would still work if the direction of time were flipped. In particle physics, this question becomes precise. Certain transformations can reveal whether a process and its time-reversed counterpart behave identically. The connection to antimatter is deep because modern physics links charge, parity, and time in a combined symmetry. If one part is violated, another may need to compensate so the combined rule survives. This is not the same as building a time machine. It is a way of testing whether nature's microscopic rules contain an arrow that points one way. When particles decay, oscillate, or transform, they may quietly reveal that time is not merely a backdrop. Some particle decays break symmetry in subtle but vital ways. A particle decay can seem like a tiny event. One unstable particle transforms into lighter particles, and the products fly away. But hidden inside those transformations are some of the most important clues in physics. Certain particles decay in ways that do not treat matter and antimatter as perfect equals. The difference can be extremely small, often requiring huge numbers of events to measure. Yet those measurements changed our view of the universe. Symmetry breaking means the laws are not perfectly balanced between every mirrored possibility. This matters because the early universe was full of unstable particles, intense energy, and rapid transformations. If decays slightly favored matter under the right conditions, they could help explain why matter survived. A minuscule bias in a particle's behavior may sound insignificant, but when repeated across the newborn cosmos, it could decide whether atoms ever formed. The fate of galaxies may have depended on details inside vanishing particles. Kaons revealed that nature treats matter and antimatter differently. Kaons are particles containing strange quarks, and their behavior opened a major crack in the idea of perfect symmetry. In the 1960s, experiments showed that neutral kaons and their antiparticle counterparts did not behave as exact mirror images. This was the first observation of a type of symmetry violation involving charge and parity together. The result was startling. Until then, many physicists believed that even if mirror symmetry alone failed, combining it with matter-antimatter exchange might restore balance. Kaons proved that nature was more subtle. Their decays showed a small but real preference that could not be ignored. The effect was not large enough by itself to explain the whole cosmic matter excess, but it revealed that the necessary kind of difference exists in nature. A small particle with a brief lifetime became a messenger from deeper lore. It showed that the universe does not always treat the mirror world with perfect fairness. B mesons helped confirm deeper violations of cosmic symmetry. After kaons revealed one crack, physicists looked for more. B mesons became a powerful testing ground because they contain bottom quarks and can decay through many channels. Large experiments created enormous numbers of them and compared how B mesons and anti-B mesons transformed. The results showed clear violations of charge parity symmetry in new ways. These measurements help confirm the framework that explains how quark mixing can produce such effects. They also showed that symmetry breaking is not confined to one strange corner of particle physics. It appears across different families of particles. Still, the amount seen in quark behavior does not seem sufficient to explain why the universe contains so much matter. That gap is fascinating. Experiments have confirmed that nature can prefer one side in certain decays, but the known preference may be too weak. B mesons therefore both solve and sharpen the mystery. They show us a mechanism, then leave us wanting more. Neutrinos may help explain why matter won the universe. Neutrinos are ghostly particles that interact so rarely that trillions can pass through your body without leaving a trace. Their antimatter counterparts are antineutrinos. The strange behavior of neutrinos makes them especially interesting in the matter-antimatter mystery. They come in different types, and they can change from one type to another as they travel. This means they have mass, although incredibly small mass. Some theories suggest that neutrinos could violate symmetry in ways that help explain the cosmic imbalance. Others propose that very heavy neutrino-like particles in the early universe decayed in a matter-favoring way. That process could have influenced ordinary matter through later interactions. The details remain uncertain, and experiments are still searching. What makes the idea so compelling is that neutrinos already behave unlike any familiar particle. If the answer to existence is hiding somewhere, these nearly invisible travelers are natural suspects. They may be quiet, but they are not simple. Antineutrinos pass through planets almost as easily as neutrinos. Matter is almost transparent to these particles. An antineutrino can cross enormous distances through rock, water, or even an entire planet with only a tiny chance of interacting. This happens because neutrinos and antineutrinos feel the weak nuclear force, but not electromagnetism. They carry no electric charge, so they do not get pushed around by atoms the way charged particles do. Detecting one requires patience and huge instruments. Scientists build detectors filled with water, ice, or other materials, then wait for rare interactions that produce a visible signal. The fact that antineutrinos can pass through Earth makes them valuable messengers. They can escape from nuclear reactions, stellar cores, and cosmic events that light may not leave so easily. They are almost absent in behavior, yet rich in information. Their silence is part of their power. They move through the universe like nearly untouchable witnesses, carrying news from places other particles cannot leave. Nuclear reactors produce vast streams of antineutrinos every second. Inside a reactor, heavy atomic nuclei split into fragments. Those fragments are often unstable and undergo beta decay. In many beta decays, an antineutrino is emitted. The number produced is enormous. A power reactor sends out a constant flood that passes through shielding, buildings, ground, and people with almost no interaction. This makes reactors useful sources for neutrino experiments. Scientists can place detectors nearby and study how antineutrinos change as they travel. These studies helped reveal key properties of neutrinos, including their ability to oscillate between types. Reactor antineutrinos may also have practical uses in monitoring reactor activity from outside, since their flow is linked to nuclear processes inside the core. The idea is remarkable. A machine built to produce electricity also produces an invisible river of antimatter-related particles. Almost all of them leave unnoticed, crossing the world as if solid matter were barely there. Antineutrinos helped scientists confirm how beta decay really works. Beta decay once presented a serious problem. When some nuclei emitted electrons, the energy of the electrons came out in a continuous range. That seemed to threaten conservation of energy, one of physics' most trusted principles. To solve the puzzle, Wolfgang Pauli proposed that an unseen neutral particle carried away the missing energy. This particle was later developed into the neutrino idea. In beta minus decay, the emitted partner is an antineutrino. Detecting it was extremely difficult because it interacts so weakly. When experiments finally confirmed antineutrinos, they rescued energy conservation in nuclear decay and opened a new field of physics. The discovery showed that an invisible particle could be inferred from careful accounting, then found through rare interactions. Antineutrinos are therefore not just exotic byproducts. They are the answer to a historical mystery about how nuclei transform. They remind us that nature can hide essential pieces in plain absence. Some experiments search for rare particles that are their own antiparticles. Most particles have distinct antimatter partners. But there may be exceptions. A particle that is its own antiparticle would be profoundly important, especially if neutrinos fit that description. Scientists search for a process called neutrinoless double beta decay. In ordinary double beta decay, two antineutrinos are emitted. In the rare version being sought, none would escape. That absence would suggest that a neutrino and an antineutrino can effectively cancel as the same kind of particle. The experiment is incredibly difficult. Detectors must be shielded from background radiation and watched for rare signals in carefully chosen materials. The stakes are enormous. If found, the process could help explain why matter exists, because it would show that lepton number is not always conserved. It would also reveal something deep about neutrino mass. The search is a lesson in patience. Scientists are listening for an event so rare that silence itself becomes part of the measurement. Majorana particles could reshape our understanding of matter itself. The idea comes from Ettore Majorana, who realized that certain particles might be identical to their own antiparticles. If neutrinos are Majorana particles, then the boundary between matter and antimatter becomes more subtle than it appears. This would not mean that all matter is its own opposite. It would mean that neutral particles with the right properties can obey a different kind of identity. The consequences could be profound. Majorana neutrinos could support theories in which the early universe produced an imbalance between matter and antimatter through processes involving very heavy ancestors of today's neutrinos. In another area of physics, Majorana, like quasi-particles, are studied in special materials, where they may help build robust quantum systems. The same name therefore reaches from cosmology to condensed matter laboratories. Majorana's idea is powerful because it challenges a simple assumption. Perhaps some parts of nature do not have a separate mirror. Perhaps they are the mirror. Positronium is a short-lived atom made from matter and antimatter. This strange atom forms when an electron and a positron bind together. There is no proton at the center. Instead, the two lightweight particles orbit their shared center of mass. It is like a miniature hydrogen atom with a heavy nucleus removed and replaced by an antimatter partner. Because the pair are particle and antiparticle, the system cannot last long. Eventually they annihilate. Before that happens, positronium can be studied with remarkable precision. Its lifetime, energy levels, and decay patterns test quantum electrodynamics. The atom is simple enough for extremely detailed calculations, yet unusual enough to reveal delicate effects. Positronium also forms in certain materials, where its behavior can provide information about tiny pores and structures. The beauty of it lies in its temporary balance. Matter and antimatter do not always annihilate instantly. Under the right conditions, they can briefly join into an atom, hovering between union and disappearance. Positronium behaves like a tiny laboratory for quantum physics. Because it contains only an electron and a positron, it is one of the cleanest systems nature allows. There is no complicated nucleus with internal structure. The two particles have equal mass, opposite charge, and well-understood interactions. This simplicity makes positronium a superb test case. Physicists can predict its energy levels and decay rates with great precision, then compare those predictions with experiments. Tiny differences could reveal missing effects or new physics. Positronium also comes in different spin states, and those states decay in different ways. One form usually produces 2 photons. Another commonly produces 3. That distinction lets researchers probe the role of symmetry and quantum rules in annihilation. Its lifetime is brief, but its scientific value is large. In the laboratory, positronium becomes a delicate clock, a measuring tool, and a quantum puzzle. It shows how 2 particles can create a whole world of structure before vanishing. Muonium has an antimatter electron circling a heavier matter particle. Muonium is made from a positive muon and an electron. The positive muon behaves like a heavy cousin of the positron, although it belongs to a different particle family and decays after a short time. Together, the muon and electron form an atom-like system that resembles light hydrogen. It is not antimatter in the same way as antihydrogen, because the electron is ordinary matter. But the positive muon gives the atom an unusual character that makes it valuable for precision tests. Scientists study muonium to measure fundamental constants, examine magnetic properties, and test quantum theory. Since the positive muon is much heavier than a positron, the atom's structure differs from positronium. Its short lifetime also creates experimental urgency. Researchers must form it, probe it, and learn from it before the muon decays. Muonium is a reminder that the particle world contains hybrid systems, where matter and antimatter-related ingredients create temporary atoms with extraordinary usefulness. Exotic atoms reveal details ordinary atoms keep hidden. An exotic atom forms when one ordinary atomic ingredient is replaced by something unusual. A muon might take the place of an electron. An antiproton might orbit a nucleus for a brief time. A positron might join with an electron to form a delicate pair. These systems are temporary, but they can act like magnifying tools. A heavier particle orbiting close to a nucleus can reveal nuclear size and structure more sensitively than an ordinary electron. Antiprotonic atoms can provide information about how antiprotons interact with nuclear matter. Each exotic atom changes the scale, timing, or forces inside the system. That gives scientists access to details that ordinary atoms do not emphasize. The challenge is that many exotic atoms decay or annihilate quickly. Experiments must catch their signals with precise timing. Their brief lives make them valuable rather than useless. They allow physicists to ask sharper questions by building atoms that nature rarely lets last. Antimatter experiments require some of the coldest conditions on Earth. Speed is the enemy of careful measurement. Newly produced antiparticles often move too fast to trap, combine, or study with precision. Cooling them reduces their motion and makes delicate experiments possible. To create antihydrogen that can be confined, Scientists need antiprotons and positrons moving slowly enough to meet without flying apart or striking the apparatus. Some experiments use cryogenic systems, carefully controlled electromagnetic traps, and techniques that remove energy from particle clouds. Cold conditions also reduce unwanted background effects in detectors and help maintain stable environments. This kind of cold is not about comfort. It is a tool for control. At low energies, antimatter becomes less like a flash of debris and more like something researchers can hold in a field long enough to question. The contrast is striking. To study one of the most energetic ideas in physics, scientists often begin by making the particles as slow and cold as possible. Slower antiparticles are easier to trap and study carefully. A fast antiparticle can cross an experiment in a tiny fraction of a second. It may hit a wall, pass through a detector, or escape the region where fields can control it. Slowing it changes everything. A low-energy antiproton can be guided into a trap. A cooled positron cloud can be shaped and stored. Slow particles give scientists time to measure, combine, and manipulate them. This is especially important when building antiatoms. If the ingredients collide too violently, they do not form the desired structure. They must meet under conditions gentle enough for binding to occur. Slowing antiparticles is not as simple as applying brakes. The techniques involve electromagnetic fields, interactions with carefully prepared particle clouds, and staged deceleration. Each step reduces energy without losing too many particles. The result is a transformation in usefulness. A fast antiparticle is evidence of creation. A slow antiparticle becomes an experimental subject. CERN antiproton decelerator gently slows antimatter for experiments. Most accelerators are famous for speeding particles up, but this machine does the opposite. Antiprotons are created at high energies after collisions, then collected and passed through systems that reduce their speed. The goal is to deliver low-energy antiprotons to experiments that can trap and study them. This requires careful beam handling. The particles must be cooled, focused, and slowed without letting them strike matter. The decelerator feeds experiments that investigate antihydrogen, antiproton properties, and antimatter behavior under controlled conditions. Its existence shows that antimatter research is not only about producing rare particles, it is about making them usable. A particle born too fast is like a message shouted past the listener. Slowing it lets scientists hear what it has to say. The antiproton decelerator turns violent collision products into manageable beams, allowing some of the most precise antimatter experiments ever attempted. Antimatter research depends on patience, precision, and extraordinary machines. The drama of antimatter often hides the real character of the work. Much of it is slow, careful, and deeply technical. Researchers must tune magnetic fields, maintain extreme vacuums, control temperatures, reduce background noise, and analyze rare events. A successful measurement may depend on keeping a few particles under control, while the entire surrounding world tries to interfere. The machines are enormous in complexity, even when the particles being studied are almost unimaginably small. Every cable, detector, magnet, and timing system has a role. The data can require months or years of analysis. This patience is part of what makes the field beautiful. Scientists are not simply chasing explosions or futuristic power. They are using the most refined tools humanity can build to ask whether the universe's mirror is exact. In antimatter research, discovery often arrives not as a spectacle, but as a tiny difference measured with extraordinary care. A single stray gas molecule can ruin an antimatter trap. Inside an antimatter experiment, empty space has to be emptier than almost anywhere on Earth. Even one ordinary molecule, drifting through the trap can become a target. If an antiproton or antihydrogen atom strikes it, the carefully prepared particle may be lost in an instant. This is why vacuum technology is not a background detail. It is part of the experiment itself. Pumps remove air until only a tiny remnant remains. Surfaces are cleaned, cooled, and designed to release as little gas as possible. The goal is to create a region where antimatter can move without meeting the material world. This demand changes the whole character of the laboratory. A small leak, a warm surface, or a trace impurity can shorten the life of the particles. The enemy is not always dramatic. Sometimes it is a single molecule, wandering through a space that scientists have spent years making almost perfectly empty. Vacuum chambers protect antimatter experiments from ordinary air. Air seems harmless because we move through it without thinking. To antimatter, it is a dense forest of possible collisions. Every breath contains vast numbers of nitrogen, oxygen, water vapor, and other molecules. An antiparticle released into normal air would not travel far before meeting ordinary matter. A vacuum chamber removes that problem by creating a protected experimental space. The chamber walls are built from materials chosen for strength, cleanliness, and stability. Pumps pull out gas, while sensors monitor pressure with extreme sensitivity. In many experiments, the vacuum is paired with cold temperatures because colder surfaces release fewer stray molecules. This allows researchers to keep particles alive long enough to guide them, combine them, or measure them. The chamber is not simply a box around the science. It is part of the science. It creates the rare condition that antimatter needs most, a place where contact with ordinary matter becomes unlikely. Lasers can probe antihydrogen without touching it directly. To study an antiatom, scientists need a tool that can reach it without destroying it. Light is perfect for this. A laser can be tuned to a specific frequency and aimed at trapped antihydrogen. If the frequency matches an allowed transition, the positron changes energy state. By watching how the atoms respond, researchers learn about their internal structure. This is called spectroscopy, and it is one of the most precise methods in all of physics. The beauty is that the laser does not need to grab the atom or place a detector against it. It asks a question in light, then waits for the atom's answer. Hydrogen has been studied this way with extraordinary accuracy. Repeating the method with antihydrogen lets scientists compare matter and antimatter through their spectral fingerprints. A tiny mismatch could be revolutionary. A perfect match would still be profound because it shows how deeply symmetry runs. The color of antihydrogen light tests the sameness of nature. Atoms do not emit and absorb all light equally. They respond at specific frequencies, which act like a fingerprint. For hydrogen, those fingerprints have been measured so precisely that they help define some of the finest tests in physics. Antihydrogen should have the same pattern if the deepest symmetries are exact. Scientists therefore examine whether the antiatom responds to the same colors of laser light as its ordinary counterpart. This is not about color in the everyday visual sense alone. It is about frequency, energy, and the spacing between quantum levels. If antihydrogen's light signature shifted even slightly, it could mean that matter and antimatter are not perfect mirrors. That would shake the foundations of known theory. So far, the comparison agrees closely. But each improvement narrows the hiding places for new physics. The question is simple enough to say softly. Does the mirror atom sing the same note? So far, antimatter behaves almost exactly as physics predicts. This may sound disappointing at first, but it is actually remarkable. Antimatter has been tested in many ways, from particle masses and charges to atomic spectroscopy and gravity experiments. Again and again, the results have matched the expectations of modern physics with extraordinary precision. That success tells us that the theories are not merely rough guesses. They describe a hidden side of matter with deep accuracy. Yet the word almost carries enormous weight. The great cosmic imbalance remains unexplained. Unknown symmetry violations do not seem strong enough to account for everything. Scientists therefore live in a fascinating tension. Experiments keep confirming the rules, while the universe itself hints that something is missing. This is why researchers push measurements to more decimal places. They are not hoping for sloppy disagreement. They are searching for a tiny, reliable crack. If it appears, it may be the first sign of a deeper layer beneath the laws we trust. The smallest difference could open an entirely new physics. Modern physics has often changed through tiny discrepancies. A small mismatch in an orbit, a faint unexpected signal, or a measurement that refuses to fit can become the doorway to a larger theory. Antimatter is one of the best places to look for such a doorway. If an antiparticle had a slightly different mass from its particle partner, or if antihydrogen absorbed light at a slightly different frequency from hydrogen, the consequences would be immense. It would not be a small correction to a textbook. It would mean that a central symmetry of nature is incomplete. New particles, new forces, or new principles might be needed. This is why precision matters so much. The experiment may look quiet from the outside, with magnets humming and data arriving slowly. But the stakes are vast. A difference too small for the senses could explain why the cosmos became a place of matter, structure, and life. Antimatter is not negative mass, despite its strange reputation. Because antimatter sounds like the opposite of matter, it is easy to imagine that everything about it must be reversed. That is not true. Antiparticles have positive mass in the ordinary sense. They carry energy. They respond to gravity as material objects are expected to do. Their opposite nature lies in specific quantum properties, such as electric charge for charged particles. A positron is not an electron with negative weight. It is a particle with the electron's mass and a positive charge. This distinction matters because misconceptions can make antimatter seem more mystical than it is. Its real behavior is strange enough without adding false ideas. If antimatter had negative mass, it would overturn enormous parts of physics. Experiments do not support that picture. Instead, antimatter shows us a subtler kind of opposition. Nature can reverse certain internal labels while keeping mass as a shared feature. The mirror is precise, but it is not simple. Antimatter does not travel backward through time in ordinary reality. There is a famous mathematical idea that can make antiparticles look like particles moving backward in time. It appears in certain ways of writing quantum theory, where diagrams represent interactions with elegant shortcuts. But this is not the same as saying a positron in a laboratory is literally drifting into yesterday. When scientists detect antimatter, they measure real particles moving forward through time, like everything else in the experiment. The backward time picture is a tool for calculation, not a scene from everyday reality. It helps physicists organize equations and understand why antiparticles fit naturally into quantum field theory. The distinction is important because the phrase can sound more dramatic than the physics allows. Antimatter is mysterious, but it is not a time traveler in the ordinary sense. Its existence tells us that time, energy, and particle identity are woven together in deep mathematics, while experiments still unfold moment by moment. Feynman diagrams treat antiparticles like time-reversed mathematical paths. These diagrams are not pictures of tiny balls flying through space. They are compact maps of possible particle interactions. Lines represent particles, vertices represent interactions, and the whole diagram helps calculate the probability of an event. In this language, an antiparticle can be represented in a way that resembles a particle traveling backward along a time direction. This strange convention is useful because it reflects the structure of the equations. It allows particle creation, annihilation, and scattering to be handled within one consistent framework. The diagrams made difficult calculations more visual, but they should not be mistaken for camera footage of the subatomic world. Their power lies in translation. They turn complex mathematics into shapes that physicists can manipulate and interpret. Antimatter fits naturally into this system, which is part of why the diagrams became so influential. They made the particle mirror feel less like an exception and more like a built-in feature of reality. That elegant idea helped physicists calculate particle behavior. The breakthrough was not only philosophical, it changed how scientists worked. Before these diagram methods became common, calculations in quantum electrodynamics could be painfully difficult. Interactions between particles involve many possible paths and intermediate states. The diagram approach gave physicists a practical way to organize those possibilities. Each diagram corresponds to a mathematical term, and the terms can be added to predict measurable results. Antiparticles are essential within this framework because they appear naturally in allowed interactions. This helped turn strange concepts into precise predictions. The results became some of the most accurate in science, matching experiments to extraordinary detail. That success gave physicists confidence that the hidden machinery of particles was being described correctly. It also showed how beauty and usefulness can meet in physics. A simple line on paper, drawn with the right rules, can help predict what happens when particles meet inside the smallest accessible corners of nature. Antimatter shows that empty space can still produce surprises. In everyday life, empty space means nothing is there. Quantum physics teaches a more subtle lesson. Fields fill space, and particles are excitations of those fields. Under the right conditions, energy can produce a particle and its antiparticle together. This does not mean objects appear from nothing in a casual way. Conservation laws still rule. Energy, charge, momentum, and other quantities must balance. But the vacuum is not a dead background. It is the lowest energy state of active fields, and those fields can respond when disturbed. Strong electromagnetic fields, high energy photons, and violent collisions can reveal this hidden richness. Antimatter is part of that revelation because it often appears paired with matter. The universe is not built from solid things sitting in an empty container. It is built from fields capable of transformation. What we call empty space is quieter than matter, but it is not meaningless. Quantum fields allow particles and antiparticles to appear together. A quantum field is not a substance you can touch, but it is one of the deepest ideas in modern physics. Each type of particle is associated with a field that extends through space. An electron is an excitation of the electron field. A positron is related to the same underlying field in a complementary way. When enough energy is placed into a field, a particle-antiparticle pair can be created. This pairing keeps electric charge and other conserved properties balanced. In a particle collision, for example, energy does not become just any object. It becomes whatever the fields and rules permit. This is why antimatter is not an afterthought. It is embedded in the architecture of quantum theory. The field view changes the way we imagine existence. Particles are not isolated beads added to space. They are ripples of deeper systems, and antimatter is one of the forms those ripples can take. Virtual antimatter helps shape the forces inside ordinary atoms. Inside quantum theory, calculations include temporary possibilities called virtual particles. These are not particles that can be collected in a jar. They are internal features of the mathematics that influence measurable outcomes. Virtual electron-positron pairs can affect how electromagnetic forces behave at very small distances. Their presence changes the effective charge seen around a particle, an effect known as vacuum polarization. This helps explain tiny shifts in atomic energy levels. One famous example is the Lamb shift in hydrogen, where careful measurements revealed a difference that older theory could not explain. Antimatter enters the calculation because positron contributions are part of the quantum field behavior. The result is astonishing. Even ordinary atoms, stable and familiar, carry subtle marks of the particle mirror in their measured structure. Antimatter does not need to appear as a free particle to matter. Its virtual role is woven into the forces that hold the atomic world together. The vacuum is not truly empty in quantum physics. The lowest possible energy state of space still has structure. Fields remain present, and their quantum behavior affects real measurements. This does not mean the vacuum is crowded in the ordinary sense. It means that emptiness is governed by rules more active than classical physics imagined. The Casimir effect is one example. Two very close conducting plates can experience a tiny attraction because the allowed quantum field modes between them differ from those outside. Vacuum fluctuations also play roles in precision particle physics. They contribute to the behavior of electrons, photons, and atoms. Antimatter appears in this story through the field processes that pair particles with antiparticles in calculations. The message is both calm and astonishing. Remove every atom, every dust grain, every ray of visible light, and space still has quantum character. The stage is never merely blank. It has properties, limits, and measurable consequences that reach into the matter we know. Particle pairs flicker through calculations behind measurable physical effects. The word flicker can be misleading if taken too literally, but it captures something useful. In quantum calculations, temporary particle-antiparticle pairs contribute to outcomes that experiments can measure. They appear as internal possibilities, not as little objects seen directly during the process. Their effects can alter magnetic moments, shift energy levels, and influence how forces behave at short distances. One of the most famous triumphs of this approach is the electron's magnetic moment, which theory predicts with astonishing precision by accounting for many quantum contributions. Some of those contributions involve particle pairs. Antimatter is therefore not only a dramatic substance that annihilates when touched, it is also a participant in the invisible bookkeeping behind ordinary measurements. The agreement between calculation and experiment is so precise that it becomes almost eerie. It suggests that the strange mathematics of temporary possibilities is not optional decoration. It is part of how nature achieves its exact behavior. Antimatter helped confirm that mass is a form of energy. Einstein's relation between mass and energy is often quoted, but antimatter gives it a vivid physical meaning. When a particle and matching antiparticle annihilate, the mass they carried can reappear as radiation or other particles. This is not merely a release of stored chemical energy. It is a transformation of mass itself into other forms. Experiments can measure the energies of the resulting photons and compare them with the mass of the original particles. The match confirms the deep connection. Antimatter events therefore act like tiny demonstrations of one of the most famous ideas in science. They show that mass is not a separate kind of stuff beyond energy. It is one way energy can be present. The concept reaches far beyond antimatter, touching nuclear reactions, particle creation, and the life cycles of stars. But annihilation makes the idea unusually direct. Matter disappears as matter, and energy carries the account forward. Einstein's famous equation becomes vivid when annihilation releases light. On a page, the equation can seem almost too simple. In an annihilation event, it becomes something physical. An electron and a positron meet, and the energy equivalent of their mass leaves as gamma-ray photons. Detectors can capture those photons and measure their energies. The result turns a line of mathematics into an observable event. This is one reason antimatter is so powerful for teaching physics. It removes the feeling that mass and energy are separate categories. The particle's mass is not merely accompanied by energy. It is energy in a form that can be transformed. Larger particle annihilations can produce more complex sprays of particles, but the same principle remains. Nature keeps the books precisely. Nothing mystical is added. Nothing is lost. The form changes. In that change, one of the deepest truths of modern physics becomes almost tangible. Light carries away what once existed as mass. Antimatter makes the boundary between substance and energy feel thin. We usually think of substance as something that stays. A table remains a table. A stone remains a stone. At the particle level, that confidence becomes less absolute. Antimatter shows that what we call matter can be transformed into radiation when it meets the right counterpart. It also shows the reverse idea. With enough concentrated energy, matter and antimatter can be created together. The two directions belong to one deeper relationship. Substance is not as fixed as the senses suggest. It is one expression of energy arranged in stable patterns. This does not make everyday objects unreal. It makes them more remarkable. Their stability is a condition, not a guarantee written into existence forever. Particle physics reveals that the universe is capable of changing form at the most basic level. Antimatter stands at that threshold. It is matter enough to be measured, but it reminds us that matter can become light. The word antimatter entered science after theory outran observation. Before anyone held experimental evidence for an antiparticle, mathematics had already suggested the need for one. The language of antimatter grew from that strange situation. Scientists had to name a concept that was not yet familiar as a material presence. The word carries the history of a prediction becoming real. It also carries a subtle shift in worldview. Once antimatter was accepted, matter no longer seemed like the only possible form of substance. It became one side of a paired structure. The vocabulary helped researchers talk about positrons, antiprotons, antiatoms, and larger possibilities without treating each as an isolated oddity. Words matter in science because they organize imagination. A good term lets a new idea become discussable, testable, and teachable. Antimatter is now a common word, but it began as a doorway. It named the unseen partner of the known world before experiments fully opened that door. Dirac's equation revealed a hidden mirror inside reality. The equation was built to describe electrons in a way that respected both quantum mechanics and special relativity. Yet it seemed to contain more than its creator first intended. Its solutions pointed toward states that did not fit neatly into the known particle picture. Rather than discard the mathematics, physicists gradually learned to interpret it as evidence for antiparticles. This was a profound lesson. The mirror world of antimatter was not guessed from mythology or visual symmetry. It emerged from the demand that two successful theories work together. That makes the story especially powerful. Reality appeared to contain a hidden partner because the equations required consistency. The later discovery of the positron confirmed that the mathematics had reached into nature ahead of direct observation. Dirac's work remains one of the great examples of theoretical physics at its best. It showed that a well-formed equation can reveal something the universe has not yet shown our eyes. Carl Anderson photographed the positron track in the year 1932. The image came from cosmic ray studies using a cloud chamber in a magnetic field. Charged particles passing through the chamber left tracks, and the magnetic field bent those tracks according to charge and momentum. Anderson saw a path that matched a particle with electron-like mass, but positive charge. A plate in the chamber helped determine its direction of travel, making the interpretation stronger. The photograph was not dramatic in an everyday sense. It was a curved line in a scientific instrument. But that line changed physics. It showed that the predicted positive electron was real. It also proved that high-energy particles from space could reveal new ingredients of nature. The discovery earned recognition because it connected theory, cosmic radiation, and experimental skill in one visible trace. A particle too small to see had written its presence in vapor, and that delicate mark became the first confirmed footprint of antimatter. Antiprotons were first confirmed in the year 1955. Finding the proton's antimatter partner required more powerful tools than the positron discovery. An antiproton is much heavier than a positron, so creating it takes far more energy. Scientists used a particle accelerator capable of producing collisions energetic enough to generate proton-antiproton pairs. The challenge was not only creation. The experiment also had to identify antiprotons among many other particles produced in the collision debris. Researchers measured properties such as charge, momentum, velocity, and mass to confirm what they had found. The discovery showed that antimatter was not limited to the electron family. Even the heavy particles inside atomic nuclei had mirror counterparts. This widened the meaning of antimatter dramatically. It suggested that entire antiatoms could exist in principle because the necessary nuclear building block had been found. The antiproton's confirmation marked a step from a single surprising particle to a broader mirrored architecture of matter. Antihydrogen atoms were first produced in the year 1995. Creating an antiatom was a landmark because it moved antimatter research from isolated antiparticles toward atomic structure. Antihydrogen requires an antiproton and a positron to come together in a bound system. The first production did not yet allow long, calm study. The antiatoms were fast and short-lived. They appeared, traveled, and vanished when they met ordinary matter. Still, the achievement proved that the simplest atom could be mirrored. This was not just a symbolic success. It opened the path toward comparing hydrogen and antihydrogen in detail. A single antiatom contains a complete miniature laboratory for testing symmetry. Its structure can, in principle, reveal whether the quantum rules for antimatter match the rules for matter. The early production was like lighting a match in a storm. Brief, difficult, and hard to hold. But once the match had been lit, researchers could begin working toward traps, cooling methods, and precision measurements. The first trapped antihydrogen appeared in the year 2010. Producing antihydrogen was already difficult, but trapping it was a different level of achievement. A neutral antiatom cannot be held as easily as a charged particle. It must be slow enough for magnetic fields to confine it through its tiny magnetic behavior. In the successful experiments, researchers combined cold antiprotons and positrons, then used a magnetic trap to hold some of the antihydrogen atoms after formation. Detection came when the trap was turned off and the antiatoms escaped, annihilating on the walls and producing signals. This showed that the atoms had truly been held. The result changed what could be asked experimentally. Instead of merely knowing that antihydrogen could exist, scientists could now keep it long enough to study it. That opened the way to laser spectroscopy and gravity tests. The milestone was quiet in appearance, but enormous in consequence. It turned antimatter atoms from fleeting products into subjects of measurement. Antimatter experiments are among the cleanest tests of modern physics. A clean test is one where the question is sharp and the interpretation is as free as possible from messy complications. Antimatter offers several such tests. Compare a proton with an antiproton. Compare hydrogen with antihydrogen. Measure whether the charges, masses, magnetic properties, or light signatures match. The targets are simple, but the implications are huge. If the results agree, foundational symmetries survive another challenge. If they disagree, physics must change. The experiments are difficult precisely because the questions are so clean. Researchers must remove disturbances, cool particles, control fields, and understand every source of error. The beauty is that a measurement involving a few trapped particles can speak to laws that govern the universe. This is why antimatter sits at the center of precision physics. It lets scientists ask whether nature's mirror is exact, not through philosophy, but through numbers measured in the laboratory. Tiny antimatter measurements can challenge theories about the entire cosmos. The scale contrast is breathtaking. A measurement made inside a laboratory trap may involve a handful of particles. Yet the result can matter for cosmology, because the same laws applied when the universe was young. If matter and antimatter differ in a new way, that difference might help explain the ancient imbalance that allowed matter to survive. This is why precision experiments are not small in significance. A tiny shift in an antiproton's magnetic moment, a tiny mismatch in antihydrogen spectrum, or a tiny deviation in gravitational behavior could send theorists back to the foundations. The experiment may fit on Earth, but the question reaches to the beginning of time. Scientists are not only measuring particles, they are testing whether the rules we infer from today's universe are complete enough to explain why there is a today at all. In antimatter physics, the smallest numbers can carry the largest meanings. Future antimatter studies may expose hidden cracks in known physics. The next advances may come from better traps, colder antiatoms, more precise lasers, and improved detectors. Each improvement gives researchers a sharper view of the mirror. They will test antihydrogen spectrum in greater detail. They will measure how antimatter responds to gravity with higher accuracy. They will compare particle and antiparticle properties across more decimal places. The hope is not to force a discovery, but to leave nature fewer places to hide. Known physics is extraordinarily successful, yet it does not answer every question. It does not fully explain the matter imbalance. It does not include gravity in the same quantum framework as the other forces. It does not identify dark matter. Antimatter may connect to some of these unknowns through subtle differences. Even a null result has value because it constrains possibilities. Future studies may confirm symmetry with greater confidence, or they may find the first hairline fracture in the mirror. The universe's missing antimatter remains one of science's greatest puzzles. The strange part is not that antimatter is hard to make today. The strange part is that the early universe should have been able to make it easily. High energy conditions after the Big Bang were perfect for creating particles and antiparticles. Yet the cosmos we observe is overwhelmingly made of matter. This missing half is not a small bookkeeping issue. It is tied to the existence of every ordinary object. Physicists have pieces of the answer. They know some symmetries can break. They know the early universe changed rapidly. They know matter and antimatter can annihilate. But the full mechanism remains out of reach. The puzzle is therefore both ancient and active. It began in the first moments of time, but it is investigated now with detectors, accelerators, telescopes, and equations. The missing antimatter is a silence across the sky, and that silence asks why anything remained. Antimatter turns the simplest question into something astonishing. The question is simple enough for a child to ask. Why is there something instead of nothing? Antimatter makes the question sharper. If nature created matter with an opposite partner, then existence was not guaranteed. The ingredients of the newborn universe may have been balanced so closely that almost everything could have cancelled away. The fact that anything survived becomes an event requiring explanation. This changes how we look at ordinary things. A glass of water, a sleeping cat, a mountain, or a human hand is not merely present. It is evidence that the early universe took a path that preserved matter. The question stops being abstract. It becomes physical. It belongs to particles, decays, symmetries, and measurements. Antimatter does not answer the question by itself. It makes the question more precise, and therefore more powerful. It turns existence from something we assume into something science can investigate. Everything we see may exist because antimatter lost by almost nothing. The victory of matter was not a grand conquest in any familiar sense. It may have been a tiny excess, a minute imbalance hidden inside early physics. Almost every particle of matter could have found an antiparticle and vanished into radiation. Only the leftover remained. From that residue came atoms. From atoms came stars. From stars came the elements that later formed planets and life. The difference may have been so small, but it would seem insignificant beside the vastness it produced. Yet the consequence was the visible universe. This is the final wonder of antimatter. It is not only a substance with opposite charge, or a tool for experiments, or a clue in cosmic rays. It is the missing competitor in the story of everything. Matter did not need to win by much. It only needed to win enough. That narrow margin became the world, the sky, and every mind able to wonder about it. And so, we come to the end of our journey through antimatter. Tonight, we followed one of the strangest ideas in all of science. We began with particles that mirror the familiar world, then watched them meet matter and disappear into flashes of energy. We saw how a hidden imbalance in the early universe may be the reason anything exists at all. We visited laboratories where antiatoms are held away from the walls by invisible fields. We looked towards storms, stars, black holes, and the deep center of the Milky Way, where tiny traces of antimatter still leave their signatures in light. We saw that hospitals can use positrons to look inside the living body. And we found that even the emptiness of space is not as simple as it seems. Antimatter can feel like a doorway. On one side is the world we know. On the other is a mirror that almost matches it, but not quite. Somewhere in that difference may be one of the oldest answers in the universe. And now, as the facts begin to settle, you can let the questions drift a little farther away. You do not need to solve them tonight. You do not need to hold on to every detail. Let the science become soft around the edges. Let the vastness of it rest gently in the background. If you enjoyed this quiet journey, you are welcome to like, subscribe, or leave a thought below. It helps others find their way here too, one sleepy soul at a time. And if you happen to still be awake, there should be another video waiting on the screen, ready to carry you into another calm corner of science. But for now, let your shoulders loosen. Let your breathing slow. Let the day fall away. And allow your mind to settle into the dark, where even the smallest particle can become a wonder. Sleep well, and good night.